So graphing rational functions. Again, you've got the handout, but we're going to take some kind of notes on our own on the back. And then we'll use those notes to fill out the graphs. I'm going to write small-ish, hopefully to fit it all on that page. All right. Rational function graphs. And some silliness with the capitalization there. It's going to be ratio fun today. We're going to put a lot of pieces together. Things that in theory you already know. A few new things, and just dump it all together and do some graphs. So a rational function is a function that is f of x over g of x, where they're both polynomials. So one polynomial over another. Polynomial over polynomial.
What is a polynomial again?
A polynomial would be anything with a integer exponent, x squared, x cubed, x to the fourth, not square roots. That would be the main thing. So most of ours are going to look like x squared minus 3x minus 4 over x plus 2, something like that. And a big chunk of getting these graphs right is understanding the difference between 0 over 4 and 4 over 0. I mean, that's supposed to be basic stuff, but obviously if you get it backwards, it's going to be a really rough day here. So what's 0 over 4 equal to? 0. And 4 over 0? Undefined. Okay, that's sort of the backbone of a big chunk of what we'll do today. If you're still having trouble with that, remember it's okay and no. If 0 is in the top, that's okay. If 0 is in the bottom, that's a no. That's the easy way to remember it if you're still getting those confused. So 0 in the top makes the fraction 0. 0 in the bottom you can't have. It makes it undefined. All right, 4 Roman numerals, but they get shorter as we go. So the first one's kind of long, but they'll gradually get shorter with each one. All right, the domain. That's the allowable x values. The allowable x values. And here's the order that we'll ask the questions. So each graph is going to have this long series of questions, and we'll ask them the same way, the same order, so that will help a little bit. The first question will be find the domain, and that will be what makes the denominator 0, or the denominator can't be 0, maybe a better way to say that, because you can't divide by 0. We've used that a few times. And then for each x that makes denominator equal 0, either, so one of two things is happening. If it makes the bottom 0, so I'm going to kind of indent this but still number it too, so that's like poor form for like outline form, but these are the questions that we'll ask. But everything you list as a domain problem is either going to be relisted as a whole. Do you know what makes a whole? I don't know if you've done this before. If the top and the bottom cancel, if there's a factor of the top that matches a factor of the bottom, and who knows, there's probably other stuff as well. But if a factor cancels, it makes a whole. Easy way to remember that is it sort of makes a hole in the equation. Like you canceled stuff out, you're missing something, there's a hole there. Thank you. What that looks like on the graph, so this one would have a hole at x equal 2. So whatever's going on in the graph, there's a hole at x equals 2. And again, that comes from denominator factors that cancel. Denominator factors that cancel. So if it's a factor at the bottom, that means it's a domain problem. One possibility is that it's a domain problem because there's a hole there. Like there's not an x value there. There's not a graph at x equals 2 because 2 is in the bottom. It happens to be a hole because x minus 2 is also in the top. So holes is one option. Or the second option is a vertical asymptote. Vertical asymptote. That would be a factor of the bottom that doesn't match anybody in the top. So it doesn't cancel. There's x minus 2 and probably other stuff in the bottom, other stuff in the top. But if x minus 2 doesn't cancel, that means there's a vertical asymptote at x equals 2. So who knows what's going on, but something's happening at x equals 2. And again, to just say it a different way, so denominator factors that don't cancel. So if it's a factor at the bottom, it's a domain problem. If it's a domain problem, then it's either a hole or a vertical asymptote. If it cancels, there's a hole. If it doesn't cancel, it's a vertical asymptote. So let's look at a brief example. And again, this will only be for this section. We're going to answer like 7 or 8 questions for each problem. But this is the first 3 questions. X minus 5 times x plus 3 all over x plus 3 x minus 2. And when you get to the graphs, like you don't have to, well, you might have it handy, but so today's worksheet, like if you look at number 7, in fact, if you look at any of them, they ask the same questions in the same order. And so domain, holes, vertical asymptotes. So we're practicing the first 3 questions here. Domain, holes, vertical asymptote. Always going to be the first 3 questions we ask. So the domain is, what can't x be? So you tell me, looking at that problem, what can't x be? What would be a problem for x? Okay, so I like that you said -3. X can't be -3. 5 is okay. But I'm glad you said it. That's the common mistake, is like, oh, just anything that makes it 0. It's like, no, anything that makes the bottom 0 is a problem. So we can't use -3 and we can't use 2. 5 is fine. 5 we'll talk about later. It makes the top 0 and that does something else. But it's not a domain problem. We can plug in 5 and get an okay answer. All right. Again, everything you list as a domain issue is either a hole or a vertical asymptote. Well, I noticed that x plus 3 cancels. What does that mean? Is -3 then a hole or a vertical asymptote? A hole. If it cancels, it's a hole. It makes a hole in my equation. So there's a hole at -3, comma something. Right? Because a hole has a y value, even though it's like a non-point. It's not really there, but there is a y value associated with it. What do we usually do if we know the x and we want to know the y? What do you usually do? You just plug it in. So we're going to plug in -3 to what's left. Don't plug it in to what's before what's left, because then you get 0 over 0, and that's why it's a hole. So you plug in -3 to what's left. So -3 minus 5 over -3 minus 2. -8 over -5 is 8/5. So there's a hole at -3 8/5. A lot of times this is a place where you get a fraction answer. These graphs are complicated and there's so much information that it's hard to write problems where all the answers are nice. Like, you guys have probably figured that out. Most of the times math teachers write the problems so that you get integer answers. Usually, then the hard problems have fractions. On these, it's too hard to make everything work out nice. So there's usually one or two things that it's like, that didn't turn out quite as well as I'd like, but that's okay. So don't panic if you get a fraction there. It just means we couldn't make it all work. Vertical asymptotes, that would be the factors that don't cancel. And a vertical asymptote, a vertical line, is an x equals line. So that would be x equals 2. All right, that's about the first third of the questions. Domain, holes, vertical asymptotes. They all go together. Find the domain, then the holes, then the vertical asymptotes. We'll always ask it the same order, and we'll always prompt you for the questions. We're not going to give you a graph or an equation and just then say graph it. Like, we're going to ask you for the pieces, and then you'll use the pieces to graph it. All right, that was Roman numeral 1. Roman numeral 2. By the way, you peek ahead, you know what's coming. Asymptotes. Well, horizontal and slant. So the next two kind of go together. Horizontal or, it won't be both, it'll be one or the other. Horizontal or slant asymptote. Always one or the other. So we will always ask for both. Again, I'm keeping this. So question D, question E. Without even looking at the problem, one of those answers is going to be none, because there's going to be a horizontal or a slant, but not both. So one of those answers will always be none. And how we tell is the degree of the top versus the degree of the bottom. The degree of the top versus the degree of the bottom. When we say degree, what do we mean by that? Which power of x? Yeah, the largest power of x. So we're looking for the highest power of the top, the highest power of the bottom, and we're going to compare those. And here's our three possibilities. It could be bigger on bottom. So let's see an example of that. 7x plus 14 over x plus 3, x plus 1. Okay, I guess the first question is, do you agree that that's bigger on bottom? Like, do you agree that the degree of the denominator is bigger than the degree of the numerator?
Yeah.
Okay, good. Because some people look at that and they're like, why? The highest power I see is x. What's the degree of the denominator?
X squared.
Yeah, that's an x squared if you multiplied it out. So that's degree 2. That's bigger on bottom. Maybe back up a little bit, and this will help some people understand what's going on. Horizontal and slant asymptotes happen as x goes to infinity. So as x gets really, really big. So if we look at this, as x gets really big, well, the top's going to get big, 7x. Bottom's going to get big, x squared. Do you know which one's getting bigger or faster? 7x versus x squared?
Probably x squared.
Yeah, x squared, because if I plug in 1,000, 7,000 is big, but 1,000 squared is really big. So this is getting really big on the bottom. So if I have a number divided by a really big number, do you know what that equals? Like if I have $5 in my pocket and I divide it by everybody in the whole world, how much does each person get?
Not even a penny.
Pretty dang close to zero. Pretty close to zero. And the more people there are, the less money they get, and it approaches zero. So bigger on bottom, y equals 0. That's our favorite case because there's no math to do. It's just bigger on bottom, it's 0. Y equals 0. Well, the opposite case would be bigger on top. So you know what? Let's just reverse the example that we just did. X plus 3, x plus 1 over 7x plus 14. The top is degree 2. The bottom is degree 1. So it's definitely bigger on top. And again, we kind of go through that same thought process. X squared over 7x. Well, they're both getting bigger, but x squared is getting way bigger. So this thing is getting too big, and this is our least favorite case because this is going to give us a slant asymptote. And that's sort of a whole separate issue, so we'll kind of table that and come back to that when we need it, how to find the slant asymptote. But the short answer is we'll need to divide the top by the bottom. So now it's back to long division versus synthetic division, all of that. Again, table that, we'll come back to it later. So bigger on top is a slant asymptote. Well, what case is left? They're the same. I'm not going to say equal, although that's good. I'm going to use a longer phrase because it's going to feed into a mnemonic device in a moment. Let's say that exponents are the same. If the exponents are the same, so let's say we have 8x squared plus 12x minus 7 4x squared minus 9. And we're trying to think what happens when x gets really, really big. So approximately, when x gets really big, we're plugging in 1,000 or 1,000,000 or probably even 100. The 12x and the 7, they're not going to matter so much. Like the only terms that are going to matter are the lead terms. So the 8x squared and 4x squared. But then that's kind of nice, because what's 8x squared divided by 4x squared? 2. So that wouldn't be y equals 2. The shortcut, though, instead of writing all that out, is to just divide the coefficients. Divide the coefficients. Pause for a second. That's Roman numeral 2. Horizontal versus slant asymptote. Maybe we should also pause and say y equals 0, that's a horizontal asymptote. Y equals 2, that's a horizontal asymptote. But obviously a slant asymptote is a slant. Now the reason I wrote them that way instead of like putting the horizontals together is because now it makes this nice mnemonic device. Bigger on bottom, you get 0. Bobo, bigger on bottom, 0. So that's a little bit confusing because the first O is an O, like the letter O. The second O is a 0. So Bobo, bigger on bottom, y equals 0. Bigger on top, you get a slant. Bigger on top, slant. And then this is what makes it funny. Exponents are the same. You divide the coefficients. Bobo Bots eats DC. It's like some dumb sci-fi movie. The attack of the Bobo Bots on our nation's capital. Bobo Bots eats DC. So Bobo's our favorite. You just get 0. Eats DC is pretty easy because you just divide the coefficients. Bots is a pain because you have to slant. And by the way, slant usually means synthetic. So sometimes people get confused on what the S means, but it doesn't matter. It means both of those things, slant or synthetic. So Bobo Bots eats DC. Again, we'll use that. We'll get used to it. We'll be okay. Roman numeral 3. Intercepts. By the way, I'm looking back at number 7 again. So the first 3 things go together. That was Roman numeral 1. The second 2 things go together. Horizontal and slant. That's Bobo Bots eats DC. And then the last 2 things are intercepts. That's our Roman numeral 3. So first, to find a y-intercept, x, y, where it crosses the y-axis. Do you remember how to find a y-intercept? Or what coordinate do you know of this y-intercept? The x is 0. So y-intercept, set x equal to 0. And x-intercepts, and there can be more than one x-intercept, so parentheses s, because there might be more than one. Right, you could have lots of x-intercepts. We've seen that before, roots and factors. You can have more than one. What do we do to find the x-intercepts? Set y equal to 0. So those two things you've done before, that's like 7th, 8th grade stuff. It's just you haven't used it in a while. Y-intercept, set x equal to 0. You won't have more than one. You might not have any, but you definitely won't have more than one. X-intercepts, you could have any number. And then lastly, almost out of room, but Roman numeral 4 is really short, because all we're really going to say is graph everything. So when you make it this far in the problem, you've got holes, you've got vertical asymptotes, you've got horizontal or slant, you've got some intercepts, you put all those on the graph, and then if needed, so it kind of depends on the problem. Sometimes you have everything you need in your graph, you can tell what it looks like. But if needed, for more points, make a table of values. So just old school, pick some x's, plug them in, see what you get. It's kind of a twist on this. Like, the harder the first 7 questions are, the good news is that means you have more information and your graph will look good. The easier the first 7 questions are, that usually means you don't have very much information and you're going to have to do some points. But we'll see what that looks like. Alright, so that's all of the information. There's a lot there, but try to break it down into 3 sections. Domain, holes, vertical asymptotes, horizontal and slant asymptote, and then intercepts. And then you put all that on the graph. Alright, so flip it over to the front. Let's walk through an example. And this, like the first example, takes the whole page because we kind of blow it up and make it really big so you can take more notes if you need to. But most of them are not going to take this much time. All right, so example 1, x squared plus 3x plus 2 over x squared minus 4. What do you think we should do first? Factor it. Yeah, we didn't say that, but yeah, let's factor it. I kind of don't like how this is laid out because I wish the first 3 were grouped together. A, B, and C. Domain, holes, vertical asymptotes, because that all goes together. So how about the domain? What can't x be? Yep, x can't be 2 or negative 2. Sort of redo the notes in abbreviated form on this. So for that, we're just looking for what makes the denominator 0. So x can't be 2 or negative 2. Does the graph of f have any holes? Yeah. And where is the hole? Because holes are factors that cancel. Again, we know that already, but I'm going to abbreviate the notes on this one as we go through it. So negative 2, how do I find the y value of the hole? Just plug it into what's left. So negative 2 plus 1 over negative 2 minus 2. That would be negative 1 over negative 4. So 1/4. So there's a hole at negative 2, 1/4. Vertical asymptotes. Are there any vertical asymptotes? What is it? X equals 2. Vertical asymptotes would be denominator factors that don't cancel. Again, you don't really need to retake the notes, but if you want to put it all in one spot with an example problem, denominator factors that don't cancel. Okay, so that's Roman numeral 1. Domain, holes, vertical asymptotes, they all kind of go together. That was Roman numeral 1. Part 2, horizontal versus slant. Again, there's always only one of those. Only one or the other. Not both. So which one is it? What case is it? Is it Bobo, Bots, or Eats DC? That's the Bobo, Bots, Eats DC. And this one's Eats DC because the exponents are the same. So is that a slant or is that a horizontal? It's a horizontal. When we DC, when we divide the coefficients, we just get one number. So y equals, what is it? 1. 1 over 1. So Bobo and Eats DC are the horizontal. The slant is the bots. So y equals 1 is our horizontal asymptote. And slant is none. Make sure you write that on the paper, on the test, on the worksheets. Otherwise, I will think you don't know. So no slants because our Eats DC, our horizontal, was y equals 1. All right, y-intercept of f. That means set x equal to 0 and plug it in and see what you get. Now, you can plug it into the original or the reduced. Usually the reduced is easier, so I'm going to plug it into the reduced. 0 plus 1 over 0 minus 2. So negative 1/2 is our y-intercept. For the x-intercept, y-intercept, set x equals 0, x-intercept, set y equal to 0. So x plus 1 over x minus 2 equals 0. What makes a fraction equal to 0, the top or the bottom? The top. So the bottom doesn't really even matter. So x equals negative 1 would be my x-intercept, negative 1, 0. All right, let's put all of that information on the graph and see if we can make sense of what we've got. So back to the top. X can't be 2 or negative 2. All right, that doesn't really go on the graph. A hole at negative 2, 1/4. So negative 2, 1/4. Put a little hole there. So the graph will go through that point, but sort of not through that point because that point's not allowed, but that's the hole. X equals 2 is a vertical asymptote. So there's my vertical asymptote at x equals 2. Let's see, next up, horizontal asymptote at y equals 1. There's my horizontal asymptote at y equals 1. I have a y-intercept of 0, negative 1/2, and an x-intercept at negative 1, 0. And And now on the left half of my graph, like left of x equals 2, I'm pretty sure I know what the graph looks like because I got 3 points over there. And I know how asymptotes work. So go through those 3 points and use the asymptotes. And so there's what the left half looks like. The right half, though, there's nothing over there. And so you might remember part of Roman numeral 4, the graph, is, well, if you don't have enough points, just make a table of values and pick some points that you want to see. So what value of x should we plug in if we want to get something over there?
Like a 1 or 2 or 3 or 4.
Well, I liked your final answers there. Not a 1, because 1 would be on this graph somewhere, and we already know what that looks like. If I plug in 2, it's not even going to work because that's an asymptote. So I need to get over into that portion, so 3 or 4 or 5. Usually if you pick 1 away from the asymptote, you get a nice answer. If you start getting further away from the asymptote, you get weirder answers, usually. So let's pick 3. And I'm going back to my, all the way up at where I reduced it to x plus 1 over x minus 2. So 3 plus 1 over 3 minus 2. That would be 4 over 1, which would be 4. So 3, comma, 1, 2, 3, 4. Now, all I need is 1 point per branch. So you have to have 1 point per branch. If you want more, you can. So if you really want to see what this thing looks like, you can plug in 4 and 5 and 6. But 1 point is enough, especially after you do a bunch of these. You'll get the hang of what they look like. So there's my graph. That's a lot of pieces. Example 2. Okay, you don't have to do what I do every time, this little grouping thing, but it helps me kind of organize and sort of makes it feel like there's less work to do. Like there's 3 main problems here as opposed to 7. Maybe. These are also great problems for popsicle sticks because you can get through like 10 people on one question. I know that excites you. So first thing we want to do is factor. So Gregory, can you factor the top for us? What do we always look for when we're factoring?
Oh, you take an x.
You can take an x out. What else can you take out?
4.
So if you take out a 4x, what's left? X plus 2. Brandon, how about the denominator? X minus 5 and x plus 2. Be careful. You probably immediately recognize that the x plus 2's will cancel. But let's not cancel them until we get to the wholes question. Otherwise, we may lose track of things. All right, our section 1 experts here. Ava, do you know what the domain of that function is? And again, we don't need to write it in interval notation. I'm fine with you just saying x can't be
5 and -2.
good. X can't be 5 and -2. Austin, are there any holes? And go ahead. he's already figured out where the hole is. So 4 times negative 2. Negative 2 minus 5. So yes, negative 2, comma 8/7. So 8/7 isn't a great answer, but it's a little bit more than 1, so we'll be able to find it. Audrey, how about vertical asymptotes?
X equals 5.
Good. All right, only get to pull one stick for D and E because there's always either one or the other, not both. This is the Bobo Bots Eats DC section. Jake, is this a Bobo, a Bots, or an Eats DC problem?
I'm not sure. I think it's wait. Would it be a Bobo because bigger on the bottom?
Bobo does mean bigger on bottom. When we say bigger on bottom, we're talking about degree.
Then I don't know. Oh, it's talking about that one. Oh, I was talking about like the.
Not the coefficients, not the factors, the degree.
I'm sorry.
So now would you like to revise your...
Yes, it is the last one.
It is. You don't even want to say Eats DC?
It
It is Eats DC. And so what do we get when we DC, when we divide the coefficients?
1.
The coefficients of the lead term.
Oh, 4.
So we get 4. I'm glad you just said 4. Don't put 4, put y equals 4, because we want it to be a horizontal line, not just the number 4. No slant asymptote. Luke, how do we find y-intercepts?
Make x equals 0.
Yes, so let's plug in 0 for x and see what we get. 4 times 0 over 0 minus 5. That would be 0. So I've got an x-intercept of 0, 0. Excuse me, a y-intercept of 0, 0. Landry, how do we find x-intercepts? Y equal to 0. So 0 equals... And again, once you've accounted for the hole, you can use the reduced function from then on out. So once you cross out the x plus 2's and say there's a hole at negative 2, then you can use the reduced one the rest of the way. So Landry, what makes me get a 0 for an answer here? I could ignore the bottom. And so what value of x makes my answer 0? 0. Well, that makes sense. If y-intercept is 0, 0, the x-intercept is 0, 0. All right, now we got to put all that on the graph. So domain doesn't really go on the graph. A hole does at negative 2, 8/7. 8/7 is just a little more than 1, so as best you can, make it just a little more than 1. Vertical asymptote at x equals 5. Horizontal asymptote at y equals 4. And the x and y intercept at the origin. All right, on the left side, I feel pretty good. I got 2 points and 2 asymptotes. So I think I know what's going on the left-hand side. If you wanted to plot more points, you're certainly welcome to. On the right-hand side, though, I got nothing. So I'm going to have to plot a point to get something over there. So I need to be to the right of 5 to get over there. So what point should we try? What x value? 6. So let's plug in 6 and see what we get. 4 times 6 is 24 over 6 minus 1. 6 minus 5 is 1. Yeah, I don't want to graph 624. That is a point on the graph, but that is way off the page.
How do you do that?
I'm not going to. I'm going to pick a different point. Let's pick 10. Just because I know 10 works. 4 times 10 over 10 minus 5. 40 over 5 is 8. 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. So 10, 8 barely gets on the graph. But we still kind of know what's going on here because of the asymptotes. All right, why don't you try number 3? I'm going to press pause. So that's what number 3 should look like. Answer all the questions, put it all on the graph, fill in some extra points if you need them. It looked like most of you were doing pretty good on this. It's a lot of steps, a lot of work. All right, I don't want to do all of these. They're all slant asymptote problems, though. That's why. So maybe we should just do number 4 and then see how we feel about things. Find the slant asymptote of that thing for number 4. Well, I mean, it asked for a slant asymptote, but how do you, if it didn't ask for one, how would you know that thing had a slant asymptote? Yeah, that's a Bot's problem. Bigger on top, slant. And preferably synthetic if we can get away with it. So 1, 0, -1, -5. And what number will we synthetic divide with? 2. Copy down the 1. Multiply, add, multiply, add, multiply, add. That last number is the remainder. Started with x cubed, we divided with x, so we have an x squared. So x squared plus 2x plus 1. No, what did I do wrong? Everyone's looking at me.
2 equals 4, right?
2 times 2 is 4 on most days. 4 minus 1 is 3. 3 times 2 is 6. 6 minus 5 is 1. There we go. We're 45 minutes deep. I'm not re-recording. We're just going to live with my mistake on video. Thank you for calling it out. So the slant asymptote, and this is maybe weird. Not maybe weird. It is weird. So you throw away the remainder. You don't need the remainder. The slant asymptote for this one is a parabola. So that means this thing's going to approach a parabola. You're not going to ever have to graph one that approaches a parabola. That's overkill. We don't want to do that. That's beyond what we want to deal with. Let's do part of number 6, and then we'll be done, because I feel pretty good that you got the hang of this. But let's jump down to horizontal and slant asymptote on number 6. So which one is it, a horizontal or a slant? A slant, because it's Bots. So that's why there's extra room for this one, because you've got to have room to divide. We'll see if I can synthetic divide this one correctly. with a positive 4 out there. Bring down the 1, multiply, add, multiply. What did I do wrong? Oh, I know what I did wrong. The problem's wrong. That's supposed to be a minus 20. That way it will factor in, everything will work out nice now. Negative 20 plus 12 is negative 8. Although it wouldn't really matter how bad the remainder is, because for these problems we just throw away the remainder. All we care about is the first stuff. So we started with an x squared, divided by an x, we're down to an x. So x plus 3 is our slant asymptote. A slant asymptote. So gotta remember how to graph a line. Surely that's not a problem. Up to 3, slope of 1. Do we need to work the rest of that problem, or we?
Wait, how did you get x plus 2?
Because my coefficients when I divided, this question was how did we get the x plus 3? When I synthetic divided, I had 1, 3, negative 8. Negative 8's the remainder. I don't really care about that. I can throw that away. Like the last unit, the remainder was like the most important thing. This unit, the remainder is like the least important thing. We want the other pieces. So x plus 3. So this one will have a slant asymptote for us. All right, your assignment is worksheet 4. As you look at it, though, you realize they're not all graphs. Like the first page is just some properties and doing pieces of it. And then you get into some graphing. I guess there's just 4 graphs that you have to complete start to finish. None of which have a slant asymptote, by the way. So that's kind of nice. And then I'll remind you that on Friday, due Friday, is worksheet 1 through 3. Not number 4, because that's new stuff. Try it. You got time left now. You still got 30 minutes left to work on it, or to finish up 1 through 3. But on Friday, we'll take questions on worksheet 4. And then I think Friday's assignment and even Monday's assignment after that are a little bit easier than this. So we put this one on block day because we know it takes a while to get through all the pieces.